Hello everyone. In this video we're going to cover derivatives and introducing a derivative, what it is, and how to work with it. So in previous sections we talked about how to find the slope of a line, and as long as we were talking about a secant line then we weren't having any trouble because we already knew how to do that. The change in y over the change in x, and that would give us the slope of the secant line. But if we wanted the slope of a specific point of a curve, then we would need the slope of the tangent line. So this became known as the tangent line problem. Because the closer the secant line is to the tangent line, then the closer we get to the correct slope, but it still wouldn't be absolutely correct because we would still be working with 2 points. So only using 1 point we have is the tangent line problem. And with that we have some things that we can go with. So in section 2.1 and 2.2, etc., we discussed that the slope of the secant line will be given by f of x minus f of a over x minus a, which is the average slope. But if we want the slope of the single point, the slope of the tangent line, that is the instantaneous slope, also known as the instantaneous rate of change, because calculus is the math of change, and slope is change as well, change in x over change in y over change in x. So the instantaneous slope is the limit as x approaches a of change in y over change in x, and this is where we get our definition of a derivative. This is what we call a derivative. The instantaneous rate of change is this lovely thing, the tangent line's slope, and this is called a derivative. So this lovely thing is a derivative. And we have several different ways of working with it and using it. So one of them, if we have the function, the continuous function, f of x, then the tangent line's slope is given by f prime of x, which is this lovely thing. We could also write it as the limit as h approaches 0 of f of a plus h minus f of a all over h, and then we would attach the limit as x approaches 0, x approaches a, to this. Okay, so this whole lovely thing is a different way of writing that. They're the same thing. So you actually have 2 different limits going on here. So we have this lovely limit here. Just move that down a little bit. So we could write this as the limit as x approaches a of the limit as h approaches 0 of this lovely thing, and this is a derivative. So now notice that we said that the function f of x is continuous. If we don't have continuity, then we don't have differentiability. You have to have one to have the other. So before we get into functions and weirdo definitions and how to apply the formulas, let's just look at graphs for a second. So let's see here. We have this lovely graph, and we want to find the values of x at which f is not continuous. Well, it looks pretty continuous to me. There's no holes. There's no asymptotes. Well, sort of. So this is continuous everywhere. But it is not differentiable everywhere because we do have these weird sharp points. Here, 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 and here. Because of those weirdo sharp points, they are not differentiable there. It is assumed that those would be as well. So piecewise functions like this one is kind of weird because yes, it's continuous, at least what we see is continuous, but it's not differentiable because we don't have a smooth curve or a smooth surface. So it's not differentiable at any of those places. Notice it says values of x. So x is not differentiable at 1985 all the way to 1990. Well, excuse me, my bad. Individually. The specific year. It's differentiable in between. It's differentiable in between just fine, just not the specific individually. Okay, so because of what a derivative is, it is the slope of the graph. All right, so we can actually do a pretty good sketch of the derivative because we know the original and we know the slope of the original. So let's see here. Each of these years, they're only 1 year apart, so I'm only going to be dividing by 1. Rise over run, right? So slope, remember, slope would be f of x minus f of a over x minus a. So all of these lovely doohickeys here. So from 8 to 6, that means I have a slope of -2 there. From 86 to 87, I'm going from 6 to 9, so that's a +3. From 87 to 88, we're going down again, so that's a slope of negative. That's 9 to 3, so that's a -6. Straight line would be a slope of 0. And then from 89 to 90, we have a positive slope again. From 3 to 6, so that's +3. So all we need to do is sketch those slopes. So we can do that quite easily. So very quickly, I did an axis here. Now I do need to go into my negative numbers because since I'm sketching the slope, I'm going to have to do so. Now, we were not differentiable at the points, so we would have open circles where we are not differentiable. So for 85, I'm going to have a open circle at -2, and that goes to 86. Because that is a linear equation, linear piece. It's going to be perfectly straight. And then I jump to +3 slope for 86 to 87. And then -6 slope from 87 to 88. Now each of those points is not differentiable, so I'm going to have an open circle on each one. And even though they are continuous, it is not differentiable at those points. So I'm going to have an open circle both top and bottom. We got a 0 slope from 88 to 89. And then a +3 again from 89 to 90. So there we go. There's the graph of the derivative, the slope of the original graph. So let's do it again. This time let's have a curve. Where is the graph not continuous? Well, as long as we're talking from -1 to 7, it's continuous pretty much everywhere except where we have a hole at x equals 5. So that is not continuous there because we have a hole. But for it not being differentiable, we also have this point here where we have this rapid shift, this pointy part. So that is an implied vertical asymptote at x equals 3, and then x equals 5, we have a hole. So when we have a vertical asymptote, it is not differentiable. The derivative does not exist. Why? Well, that's because the limit does not exist. The limit as you approach from the left and the right don't equal each other. So the derivative itself will not exist. Pardon me. So for sketching a graph when they don't give you the function, well, in our first example, all those pieces were linear, so we could do the slope very easily. For this one, not as much, and not as well, and not as easily, because they don't give us the absolute function. They just give us a kind of hand-wavy, hey, this is what happens. So instead, we're going to have to make some guesses. So this is really where the word sketch comes in. So my x-axis will be the same. So -1 all the way to 7 is what I need. Alright. And then from here, yeah, it's more hand-wavy. So I'll just say it's going by 2's on my y-axis just to get me some easy. For the graph of the derivative, now think about it. This first piece here is a parabola. It's an upside down parabola. So the function should be somewhere around -x²-ish. So I know the slope is going to be negative, and it exists at x equals -1, but the derivative does not exist at x equals 3 because of that vertical asymptote. So I'm just gonna guess. So let's say I have a solid point there, and then it is decreasing, and we have a 3 not differentiable, and just connect the lines. That's as good as it's going to get. So for the next piece, we're going to do about the same, and it is a little bit easier, as in it's less, right? So that we have a bit of a steep curve from -1 to 3, but the curve from 3 to 7 is less steep. So the slope will be less steep, but it will still be negative. So instead of this sharp point, we'll have it a bit more like that. But we still have our not differentiable points. So we'll say, how about there? And for the 7, how about there? And this is much less steep than from -1 to 3 because the curve is less steep. Now this is really a sketch. It's a sketch in that we're using the definition of the derivative, as in the definition that this is the slope, but for exacts, it's very hand-wavy. For the exacts, we need the function. So the function is where our next example comes in. So we want to use the definition to find the derivative of x squared minus 5. So the definition is the limit as h approaches 0 of f of x plus h, or a plus h, either way, x plus h minus f of x all over h. Those of you who remember your college algebra, this should look vaguely familiar. It's called the difference quotient. It is the precursor to a derivative. All we got to do is tack on the limit and you have the derivative. So f of x is given to us, we just have to figure out the rest of it. So f of x plus h take the lovely x plus h, put it into substitute, and go from here. So we have, FOIL that out, will give us x squared plus 2xh plus h squared minus 5. We can drop the parentheses easily enough. Now we can subtract f of x. So that tells us to subtract x squared minus 5. Distribute the negative. Negative times a negative is a positive. At this point, you should be able to cancel things out. If you can't, you've made an oops in your math, go find it. So we can cancel out the x squareds and the 5s, which leave us with 2xh plus h squared. And we can now apply the over h part. Alright, so that gives us anything over itself is 1, so those h's cancel. And h squared over h, that cancels out one of those, leaving 1. So we have 2x plus h. And now we can apply the limit. So the limit as h approaches 0 of 2x plus h. We spent the entirety of last chapter learning how to do this just so that we could do the derivative part. So 2x isn't going anywhere, and the limit as h approaches 0 would just be 0. So that gives us 2x. And this is our derivative. So you have the derivative as an equation, and you also have the derivative at points, individual points. Alright, so there's several different kinds of derivatives, but the most general version is this. So f of, and that tick mark there is the first derivative. So f prime is also what it's called, of x is the limit as h approaches 0 of f of x plus h minus f of x all over h, the equation itself. Now once we have the equation of the derivative, we can actually use it. So find the slope of the tangent line of f of x, well, that lovely equation we were just doing, at the point, single point, -3, 4. Well, this would be the limit as x approaches -3 of 2x, our derivative. We learned how to do this in previous sections. So 2 to the -3, so our slope, just the slope, at this point is -6. Simple substitution. For the equation of the tangent line, we have to dig out our college algebra again. It's been a while, but we've done this before. The equation of the tangent line, or also known as the point slope form of an equation, so that is y minus y1 equals mx minus x1. So we have all the information we need to be able to do this. So the point itself, that's the negative 3, 4, that will go there and there. And then the slope, well, we found that, the negative 6. So input, so y minus 4 equals negative 6, x minus negative 3. All right, careful of your negatives. And solve for y. So y minus 4, negative 6, x plus 3, negative 6x minus 18. So add 4 to both sides. Negative y equals negative 6x minus 14. So from the basic definition of the derivative, we got the equation of the derivative. Then you can use that to find the slope at a single point, and then we can find the equation at that point. So the equation of the tangent line. So the instantaneous rate of change is the limit of the derivative. All of those things work together.